So the next talk by Professor Heather Lewandowsky from the University of Colorado Boulder. So she's a professor of physics and a fellow of GILA there. She serves as faculty director of the QBIT, CUBIT, quantum initiative focused on education and workforce, so very relevant to this conference. She leads two research programs, one in experimental molecular physics and the other in physics education research. So her physics education research program studies ways to increase students' proficiency in experimental scientific practices, as well as research in the area of quantum science education and workforce development. Again, extremely relevant to what we've been talking about. So Heather, oh, there you are. Hello. I hope it's not too early for you. So please go ahead. Go ahead.
Great. Hopefully you can all see my screen now.
Yes.
So thank you very much. I'm very honored to be able to speak to you today. Unfortunately, I was unable to travel there because I'm at another conference. But I'm excited to tell you a little bit about quantum education and workforce development and how do we think about this going forward as quantum becomes sort of more relevant to our everyday lives. And so today, I'd just like to talk to you about two things. The first is looking at some studies of the quantum workforce. You know, what are the opportunities for our students going forward in terms of different jobs and skills that they need to be able to be successful. And then I'll give one example of a course that we are running at the University of Colorado where we're trying to look at those skills and say, how can we empower our students through a project-based course to really gain these skills and be prepared to enter the workforce. So I'd just like to talk a little bit about some workforce studies to give some data to back up our course transformations. And so actually, let me start a timer here. I wanted to make sure. So the first study was actually done a few years ago now, where we interviewed people in the quantum industry. There were 21 people in 2019. And then we went on and looked at a survey of 56 companies. These are primarily in the US, although they now have really sort of reached out across the world. And then the third study, which is currently ongoing, where we're actually interviewing 200 members of industry, of looking at what are their jobs like, what kind of skills and knowledge do they need to be successful. And so there's complementary work by Rainer Müller and Francesca Greinert in the European context, and we're finding very similar things. And so hopefully these ideas really translate across the world. And so first I'd like to tell you about just some of the outcomes from these studies that might be interesting to think about when we're thinking about preparing our students to enter the workforce. So one of the questions we wanted to answer was, what jobs currently exist in the quantum industry, and what are those distributions of jobs predicted to be? I think it's really important to understand if we're preparing our students, we don't want to prepare our students just for one job, but for a career and the long-term sort of success. And so what we have here is we got from a survey where on the left here is all the different job titles that we got from job ads at that point in time. And we asked people, were they going to be hiring in the next 2 years or the next 3 to 5 years in these different types of job roles. And you can see at the bottom the number of companies that said they were going to be hiring. And so I think the important thing to look at here is that the blue bars and the orange bars are basically the same length. In other words, their prediction of where they were going to be hiring wasn't going to change dramatically. And so as we prepare our students for these different jobs, we can feel somewhat confident that there will be jobs available in that sort of domain for them going out at least into the near future. Very hard to predict in quantum beyond 5-6 years. Another thing we wanted to know is what degree levels are needed for the different job types. Do we just need PhDs, or are there other types of levels that we need to think about? And so what we found was very encouraging. So what we have here on the left are the same job titles. It doesn't matter exactly what they are. And this is the percentage of the different types of degree levels the companies were hiring in. So this sort of purple is a bachelor's degree, a master's, and a PhD in here in green. And so you can see it really depends based on the job role. If you want to be an error correction scientist, you really do probably need a PhD. However, there are many roles that require just a bachelor's or master's degree. Data scientist, control systems engineer, application solutions architect. There's many different roles. And so this allows us to think about how do we prepare not just PhDs, but also our bachelor's and master's students really to enter the industry. Another question we wanted to answer is what skills are commonly needed across the quantum industry? And I'll get a little bit more to this with our third study, but this is now across all quantum jobs, not a very specific job. And I will note that this is in 2019, and I will point that out because the number one sort of skill that folks were talking about was coding. This is not coding on a quantum computer, but classical coding. Really, from my conversations currently, this has really changed with the advent of AI and machine learning methods. So that one you might have to think carefully about. But then if you look at the next 4 common skills across quantum jobs, statistical methods for data analysis, laboratory experience, electronics, troubleshooting, and problem solving. These are all very hands-on experimental skills, and those are very common in quantum jobs, and we'll see that again later. So we have to think about how do we prepare our students with these skills. And in many ways, the nice thing is these aren't very quantum specific. And so if we prepare our students with these skills, they can enter not just the quantum industry, but all sorts of types of jobs. Another question is really getting at this quantum part, of these, do quantum related jobs require a broad or narrow set of skills, and how many of those are really quantum? And so we looked at all the different skills. Once again, on the bottom, these are just all the different job roles. And this is the number of consensus skills. So we asked companies about the number of skills. And if a company said, more than 50% of the company said, this is an important skill for that job, then we counted it. So you can see for some job roles, many skills are needed. Once again, error correction scientists, there's quite a lot of primary skills. It just really depends on the job role. But these are all the skills. And then the question is, how many of these are really quantum specific? These are the ones that are quantum specific. You can see, although there's a lot of consensus in terms of the skills, not all of these are quantum, right? And so, yes, students do need some of the quantum skills depending on the job role, but there are other skills that we need to be preparing our students for. Finally, are there well-defined categories of jobs based on skills and knowledge? This will help us as students are interested in different components of the quantum industry. And so we looked at a correlation between all of the different skills. There's a lot here. I don't expect you to be able to see this. It's very hard to present on a slide here. But these are all the different types of skills or knowledge here. Cryogenic components, analog circuit design, systems architecture, error correction on both axes. And then we looked at the correlation between these different skills, so read our positive correlations. And you can see that this actually has this block diagonal structure where you see groupings of skills that are important for jobs that are all very much correlated. And then if we dig into what are the skills that are all within these individual blocks? The first one up here is basically what we could call a hardware tract. Right, so we have mechanical assembly, condensed matter physics, modeling and simulation, electronics, control theory, device physics. These are all correlated. So students and job roles, have many of these different kinds of hardware skills. And then if we look at the small box in the middle, which is often forgotten, This is sort of product development, business development, sales and marketing. So this is more of a business type role within these companies. And then finally, the box down here are really sort of more software and algorithms development, error correction, and software development. So I think it's important to know that students don't need every single skill. They can sort of focus on maybe a hardware, business, or software track. And these were data for about 5 years ago now, but we're not seeing wildly different things. So this is good that they can really focus based on their interests and think about gaining skills in sort of one of these areas. So overall, if we think about, what new preparation needs to be provided for our students, so generally what we're hearing is that companies are satisfied with the skills and knowledge of physics PhD graduates. We really don't need to wildly change those programs. They have the skills and knowledge to be very successful. They also generally highly value hands-on experience across all levels, from the bachelor's on up. And it was a theme that we heard again and again. And that's partly where the sort of industry is right now. We're building quantum sensors and things like that. It's really in the R&D phase. Other things that we saw was, recommendations for sort of undergraduate engineers, right? We don't need to build entire new programs in quantum engineering. You can have a basic course in quantum information, maybe with 2 possible tracks, one in software for computer science and software engineers, and maybe a hardware track, a course in device physics, qubits, and control electronics for electrical, mechanical, and optical engineers. We still are hearing that companies want a great RF engineer who also knows just a little bit of quantum. So it's not completely changing our undergraduate curriculum, but just maybe adding a couple of courses. So I think that is a lower bar and less of a barrier to achieve. When we think about our undergraduate physics students, the physics degree is already quite valuable, but it could be sort of more valuable to the industry if students were able to more effectively work collaboratively on software, using, not sort of the classic thing is don't program like a physicist, program with proper sort of architecture, using collaborative software. There's also maybe get a few engineering and system design skills into the physics curriculum. And this key is working on interdisciplinary teams, not just working with physicists, but with engineers and people in a variety of different disciplines. So I just wanted to point out these 3 things, this idea of hands-on skills and working in teams and design skills, because I'm going to show you how we sort of attempt to integrate that into our curriculum. Additional recommendations for students and postdocs. The quantum industry is really growing, and there are a variety of positions available, and not all require a PhD in quantum and very specialized quantum knowledge. Hands-on experiences is really desired. So getting any experience in internships, research experiences, formal lab courses are very useful for many roles. Not all in quantum information science and technology need a PhD in quantum physics, right? So just becoming sort of quantum conversant so you can have a conversation about quantum by taking just a couple of courses to have that base knowledge is really, can be empowering. Still focus on traditional STEM skills. They're really still looking for people who have those experimental hands-on skills that really translate across different disciplines. And finally, don't worry about trying to become a quantum engineer. Lots of folks want a quantum engineering program. We interviewed 21 people, and I believe we got about 26 different definitions of what a quantum engineer is. It's very ill-defined, and so don't worry about that title. Think about the skills and knowledge rather than the title of the job. So once again, I just want to point out this hands-on experience because this comes up again and again, and hopefully I'll show you just one possible way to address this. So those were 2 previous studies. Right now we're doing a much broader, in-depth study on quantum education workforce across the US, but hopefully some of these ideas will translate. And the real goal of this is to provide data-backed insights to guide educators and program developers, really to support students being well prepared and have a diverse quantum workforce. There are two components to this. The first component is a study of quantum education opportunities at the undergraduate and graduate level, and I'll show you a resource that might be useful. And then really this expanded study of the quantum workforce needs, both in industry and government labs. So the first component is what we did is looked at a landscape of quantum education in the US. So we have cataloged around 9,000 courses and all quantum information science and engineering minors, tracks, concentrations at nearly 1,500 colleges and universities in the US. Now, you may ask, why is that useful outside of the US? It could look as a resource for folks if you're looking to develop a course or a program. We have this interactive database, which I'll show a QR code here in a moment. The idea is all of these data have been put on this interactive database that you can either work with online or download. And it gives you, so on the side, you can look at courses with quantum topics. So you can go over some course, here you can move your cursor over here to Rochester Institute of Technology, and all of the different courses will pop up. And so you can go look at the description and a website, and so you could go there and say, oh, this course looks interesting. I want to develop a course, something like this, and get information directly from this database. You can look all the QISE programs in the US. So, I want to think about a master's program. What are the master's programs, and what kind of courses and structure do they have? So this is a database of all of this information. So hopefully it will be useful for folks thinking about this, because we don't want to start from scratch. If folks have already developed courses or programs, it's great to leverage those and take resources to develop new programs across the world. So this is a QR code. I'll have another one right at the end of the talk, but this is a open source database that you may be interested in if you're thinking about what else is out there in terms of courses and programs. And really what I mean by programs is anything from a track within a program, a certificate, a minor, a major, all of these different things. So that might be a resource. In addition to this current project, looking at the quantum education, we're also looking much more deeply at industry needs. So basically looking at the knowledge, skills, and abilities that our students need to have to be successful in different roles. So the goal is 200 interviews. This is quite a lot. Currently we have 37 interviews across companies of all sorts. And so this is, like 40 hours worth of data. I'll give you some initial results from this, but more will be forthcoming. And so what we looked at is all company types, from, people developing new hardware, algorithms and software, sensing, communication, enabling technologies, folks that are building cryogenics and lasers, as well as end users and people and consultants. We have two types of interviews. We looked at managers to get a broad overview of the various types of roles within that company. And then we followed up with interviews of individual employees that can speak to the specific tasks associated with their specific role. What do they do in their job? And what skills and knowledge do they need to be able to do those tasks? So just some initial results, and these are quite early because we're just in the beginning of this project. But one of the things we wanted to ask is, what specific roles don't require a PhD, right? That's where we're trying to focus. And what are the associated experimental skills for these roles? And so just to give you a snapshot of what that looks like, what roles don't require. So this is up through a master's degree, but mostly, bachelor's as well. We have 70 different roles that are described in our 37 interviews. This is because the managers described many different roles, not just their role. And so of those 70 roles, 22 of them required up to a master's degree. And these degrees included physics, engineering, computer science, and chemistry. So overall, in our current data set, which will be growing, still most of the jobs do require a PhD. That might be a bit of a bias based on what people thought of initially when we said, let's describe a quantum job. But at least we have 22 that we can really investigate in terms of what roles and what skills they need. So here are some examples of roles that don't require a PhD. So this is sort of a general classification system that we're working on, where we can see sort of a hardware box, software, and then sort of non-technical. In terms of the jobs that don't require a PhD, sort of in the hardware box, we have a lot of product development, where we say they're quantum proficient. So this is, a bachelor's, maybe a master's degree. They're developing maybe a quantum computer or a quantum sensor. There's also product assembly and testing is an opportunity, and operation and maintenance. At some point, somebody needs to be able to operate and maintain these quantum computers or quantum sensors. Additionally, both classical software and quantum algorithm development have some components that don't require a PhD. And on the non-technical side, we're seeing a lot of leadership positions, maybe product managers and various folks that don't need a PhD. So when we look at those roles and say, what are the associated experimental skills? Because what we're finding is most of those jobs have an experimental component to them. We use the AAPT, which is the American Association of Physics Teachers, recommendation for the undergraduate physics laboratory curriculum. This is a set of guidelines of thinking about all the experimental skills that we would like our undergraduate students to gain during their undergraduate career. And so we use this as a categorization to think about what skills do we need in the quantum industry. And so we look at the distribution of these experimental skills within those 22 roles that don't require a PhD. So you can see how many of the roles, what did they really need? So basically almost everybody mentioned how important communicating physics was. That was the number one. Also developing technical and practical skills, designing experiments, a few with modeling and analyzing and visualizing data. And I'll dig into a few of these to give you an idea of what sort of skills these are. So let's first just talk about communicating physics. So here's an example. For the role of test and integration engineer, somebody said, communication is key. You have to be able to communicate the tasks you've accomplished to the up and downstream teams, that the integration is complete. Really, the communication is huge. You have to let people know where you are, roadblocks you have, and the help you need. So this was really, sort of classified as communicating physics, and also collaboration is an important part you see already within this quote. In addition to communicating physics, many people mentioned technical and practical skills, which maybe is not super surprising based on the hardware nature of these job roles. If we dig into a little bit more detail of what that means, here are some of the sub-themes that we're seeing. And this is very early days in terms of our analysis, but what we're seeing is people just talking about students need some laboratory experience. That is key. They really see that working with both electronics and optics can play a major role, making measurements and understanding measurements and measurement uncertainty. How to choose algorithms and computational tools to model their experimental system. And then thinking about how to debug, test, and validate classical code. So these are some of the themes that we're seeing that are important for our bachelor's level students. So here's an example. For the role of laser and optics engineer, one person said, I would just say optics experience. A lot of our employees did have a bachelor's in physics, but they worked in an undergrad atomic physics lab or something, doing some optics. Or maybe they were similarly in chemistry, doing some optics undergrad chemistry experience. That is often a differentiator when hiring for this role. So you can see this idea of developing technical and practical skills and working with optics was important. And having that bit of undergraduate research really allowed that person to get that job. So preliminary results from this is that PhD in our data set still, PhD is preferred, but there are opportunities for folks with a bachelor's degree. And the other thing is experimental skills really do matter for these roles. The quantum industry for the bachelor's master's really requires strong experimental skills, really spanning the full scope, which is hopefully traditionally covered in the undergraduate lab training. So those are some initial results from that study. If you think about what are these implications for educators, the hope is that at undergraduate and master's level, we should really have a strong emphasis on labs that teach skills. And these skills gained in labs, even if they don't have to be explicitly quantum focused. They are skills that are needed in the quantum industry that don't require a PhD. So they don't have to be quantum labs, they just have to be labs. So those are the 3 workforce studies that either were completed or ongoing. And based on that, this idea of experimental skills, working on interdisciplinary teams, and thinking about experimental design, we designed a new course called Quantum Forge. And the course goal is to have bachelor level students learn about and be prepared to enter the quantum workforce. So these are students who are not going on to graduate school. And the reason we did this is a quote from our earlier studies. One of the industry folks said, we want people who can design an experimental program, go and implement it, take the data, understand what the data says, and then decide what the next steps are. In other words, that entire experimental process that maybe is not so typical in an undergraduate lab. So the idea is Quantum Forge is a team of 4 to 5 science and engineering students working on a 2-semester project from industrial partners. And I'll tell you a little bit more about that. And so the idea is, if we're thinking about authentic research training, there's sort of a spectrum of this. Often we think of lab courses on one end here, which are very guided, maybe very prescriptive in terms of what they have students do. There's an outcome is known. You're going to measure little g or the mu on lifetime, but they're very scalable. You can have lots of students participate. On the other end of the spectrum, we have undergraduate research where somebody works maybe in a lab of a researcher. It's open-ended, outcome is unknown, but it's very limited. There's a lot of barriers for students to participate. There just aren't a lot of opportunities, and students have outside obligations, maybe family or caring responsibilities that don't allow them to participate. And so our hope is to have something in the middle. This is where Quantum Forge really lies. The idea is it's open-ended, the outcome is unknown, but it's a bit more scalable because it is a course that students can take to satisfy some of the requirements for their degree. And so this is hopefully the space that we're trying to build out to lower the barriers for students to gain these skills that's not outside their curriculum, but is more open-ended and gives them the skills to be successful in the quantum industry, but honestly, in any workforce in high tech. So what is this course? It is a 2-semester course. It's been running for 3 years now. Typically 4th year physics and engineering physics capstone course. So this is usually the final year of their bachelor's degree, whether that's a 3rd or 4th year, depending on the country, you can sort of translate that. Students are enrolled who are not planning on going to graduate school or onto a PhD or master's. They want to go directly into the workforce. That is what this course is for. And so what did they do? Well, students, they worked on an authentic quantum industry project. This project was proposed and funded by the quantum company. They collaborated on teams of 5 to 8 students with that industry partner. They met with that industry partner once a week. And they really learned about both those quantum skills, but also the quantum industry and how to be successful in it. And so our first project, the first year, now we're actually into our fourth year now, was working with Maybell Quantum, and they make cryogenic dilution refrigerators pictured here. And the project the students were working on was to improve ultra-low temperature heat exchangers down here in the stack. So it's a very mechanical engineering type project, but has direct relevance because you need these dilution refrigerators to make a lot of the qubits work. So the course was about 5 hours per week for the students. And every week they worked on the project. They met 1 hour a week with their industry contact. They met with the instructor of the course, and they had a variety of different components of questions. And then occasionally, because of where we're located in Colorado, they were able to visit local quantum companies. That was a really nice component that, we're just very privileged because we have a lot of these companies right around the area. They had some instrument electronics training, some professional development, thinking about how to write a resume, how to interview, how to work on teams, various different kinds of professional development skills. And they had sort of remote guest speakers from industry talk a little bit about what their job was. So as we look at this course, we want to evaluate its effectiveness. And I'd just like to tell you very briefly 2 components. One is, how did students engage in teamwork and collaboration in the course? As I mentioned before, working on interdisciplinary teams is so critical, and communication is critical for being successful in the industry. So we wanted to see how students were doing in the course and how they were learning these skills. And then also after the course, what are students' perceptions of the quantum industry? This is important because this is what we're preparing them to do. So let's dig into the teamwork and collaboration first. So we looked at teamwork in this Quantum Forge course. The first year we had between 8 and 14 students, it depended on the semester. Students were each assigned 2 team roles based on their preferences. So things like product manager, test lead, electronics lead. And then there was a variety of peer feedback surveys to understand how well the team was working. And some professional development related to how to communicate, but the instructor was fairly hands-off in terms of sort of directing how they organize their team. So if we look at the student experiences, assigning these roles didn't work all that well, because not all team roles were useful, because they were assigned before everyone understood the project. And students, even if they were assigned a role, ended up working on tasks they had prior experience with, or they felt confident in those. We did find a team of 5 worked much better than a team of 8. It was too many with 8. It was hard to do. So we found some challenges there with doing the assigned roles. But looking at how students work together to understand how we can better structure this, students really divided tasks based on prior skills, interest, and ability. This we've seen in many different contexts. And so this really leads to effective projects because people already have those skills, but then students maybe don't learn some of the other skills that they don't have. They then came back together to share that knowledge and skills. So here's an example. This is a quote from an interview with some students. "My experience with teamwork as a whole has been good during the project. I think the best part of our teamwork has been teaching each other our skills and strengths. So everyone is caught up where they need to be in the project. Everyone does what they're good at and tries to help others who aren't as good through the process." So this picture off this side is some students. One knows a lot of computer-aided design and is helping other students learn that. So they were actually sort of teaching other these different skills. As we all know, teaching really helps you to actually bolster your own skills. So this was a positive outcome. They also found this is sort of a unique opportunity to collaborate that wasn't available to them in other courses. This kind of collaboration was new for some students. One student said, "In an effort to focus on my classwork, I've been pretty isolated from everyone except the coworkers I've met through lab work. I'm really excited to get to work with this larger group on something and maybe make some friends through the process. So in the rest of their curriculum, their theory courses and lab courses, they really felt fairly isolated, but because this was really this team project and was a whole year, they really got to build that collaboration and even friends through this process. So students acknowledged teamwork was essential for this project and even became friends with their team. And I think it was less isolating for them within their curriculum. So sort of summary of what we've learned, we have now implemented this in future years, is students had mostly positive experiences with the teamwork, but we had to consider a mechanism to encourage students to take on tasks and roles they're not already familiar with. This would allow them to build more skills. And so we've had students now define their own roles and then rotate through those roles. And students did need more sort of scaffolding or more guidance to learn how to work on a team with an industry partner. So we've added some components to say, how do you communicate with your industry partner? So that's where we looked at teamwork and collaboration. And another thing we wanted to look at is, after the course, what are the students' perceptions of the quantum industry? So through a variety of interviews and reflection questions that they answered at the end of we got some basic themes that we heard from students. One of the things that students said was that the breadth of the quantum industry, they thought, oh, it was just quantum computers. That's all the quantum industry was. But now they realize that there's all sorts of different roles and different types of technology. And they were excited by that because some of them didn't want to build a quantum computer, but were really excited about cryogenics or lasers. They acknowledge that there is a lot of hype, right? There's a lot of hype surrounding the quantum industry, and I'll show you how that plays out here in a second. So they acknowledge that. They really felt that this idea of lab work was an important part of the quantum industry. I know, at least in the US, sometimes students are not always excited for laboratory courses, but they really saw the use and the value of that for future jobs. They noticed the lack of diversity in the quantum industry. They were interacting with basically exclusively white men. And every single person noticed that and felt that that was actually a problem. And they weren't even sure if they wanted to enter an industry that didn't have more diversity. They felt it was a little less complicated. It was a little overwhelming before they came in, and they're like, oh, well, this is less complicated. I can actually see myself in this industry. There's a role for me. They also acknowledged there were many unknowns, right, about the future. And this goes to the hype. They were a little concerned about what are the possible long-term sort of future of the quantum industry. Is it going to be as large? Is it going to lead to all the things that people say? Just a few more things. They acknowledge it's still mostly startups at some level. They felt that it requires a PhD, which is interesting, but this is because they basically interacted with PhDs at the companies. Even though now, even from the first cohort, 2 of the 5 students who went through the course actually interned and then now have permanent jobs at that company. So that we feel is a success. And they have a bachelor's degree, but their perception was it requires a PhD. They understand that it really requires teamwork. Right? Sometimes students also are not excited by teams in coursework, but reality is the world is collaborative and must require teamwork, and so they saw that as a value. They also looked at sort of the specialized knowledge. It does require some specialized knowledge in quantum and in experimental physics. And finally, this project overall, they felt that this working on this authentic project for this course is really similar to working in the quantum industry, and they really were essentially working with that company. So overall, that course is continuing on. what are some of the things that we're doing going forward? Well, we want to continue interviews and analysis on our broad workforce study of our 200 interviews to get very specific skills for each type of job role. So if you say, oh, I want to be, maybe an optical engineer, what are the skills that I need? And we should be able to have a list of those skills, knowledge, and abilities to gain to be successful in that. We want to look further at this Quantum Forge course. It's now run for multiple years, and understanding the outcome of that. We have a longitudinal study where we're looking at students now a couple years into their career and what they perceive the impact of this course on that. And then finally, we're sort of examining other PhD education because that's an important thing in Europe. So the team that did all of this, this current work, we have two postdocs who are working on this, Andy Pina and Shams El-Ladawi. Ben Zwickel and Bethany Wilcox are some other faculty working on this. And on the Q-Forge, Kristen Oliver and postdoc Tori Borish. So here's a QR code that links to the database, but all of our quantum education research. We have papers, we have resources, all of the workforce stuff is there. So if you want to learn more, you can go there, or also, I'm happy to take questions. And also if you afterwards, if you want to email me, I'm excited to chat with anybody. Thank you.
Thanks very much, Heather. That was a really information-packed lecture and a lot of great points. All right, so it's open for questions. Anybody? Who's got their hand? Okay, got one.
Concerning the workforce, does your place of study affect the employment? Let's say I acquire a degree in quantum mechanics in Ghana here, and I apply for a job in the US. Would the company consider my place of study before employing me?
Right, so that's a very good question. I think it's a really dynamic situation right now in the US. So would a company consider folks sort of outside the US for roles? My understanding, at least, some initial comments, it is becoming more challenging for folks outside the US to gain visas to the US. That is unfortunately a terrible problem. That being said, the quantum industry is desperately looking for talent. Right now, they are struggling to get people into these roles because there's just not enough people with these skills and knowledge to be able to fill these positions. So it's kind of I'm not sure, right? It's a challenging time and things are really dynamically changing.
All right, thank you, Prof, for the presentation. It has been a very wonderful one. There are two questions I have for you. The first one is, how do we bridge the quantum divide, especially between the advanced countries and the developing countries like Africa? I could see we have a long way to go. So what are your suggestions on how, or recommendation on how to bridge the gap of what we call quantum divide? And secondly, will you advise for students to go online and take courses on quantum, and they will get the best out of it compared to the process you have in your university, where you have a collaboration with an industry? Your student can go there and have contacts with those in the industry so that they can be able to get the best out of the program. So will you advise strictly online? Student can do that, still get the best in our own context. Thank you very much.
Yeah, thank you for those questions. They're really important. How to bridge this divide. I think hopefully maybe this event is the first one of how do we build partnerships between folks in different countries? Because I think there's great opportunities to build those partnerships where we have more resourced institutions and less, and how can we learn from each other to provide sort of educational opportunities for our students. How we shouldn't be going this alone. We should think of how we can build those partnerships. And I think this comes down to this online versus, sort of in person. There are some, it depends on what skills you want. I think, some online education really can meet those skills, not all of them, right? Some of the interdisciplinary teams and things like that. But, are there opportunities where we can connect students from different institutions, remotely to start building those sort of collaborations? A lot of collaborations are not necessarily in the companies altogether. These companies are dispersed throughout the world. There may be some in Boulder, but also they're in Australia and Europe and things. And so building those collaboration skills on a remote basis is actually a skill that companies are looking for. And so maybe we can think about how we can partner with different institutions in different countries, even on a more remote basis. It's a real challenge. Don't have any real answers, but maybe we should try some things and see how it goes.
Okay, thank you very much. And please, my question is, how do we provide hands-on experiences in KYSE education here in Africa, especially with the LMICs? How do we actually do that? Because we lack a lot of resources, infrastructure, and all that. Are there better simulations we can do that kind of like mimic real-world experimentations that we can play around with here in our training?
Yeah, no, that's a great question. If the hands-on experiences, how many resources does it take? I think one of the interesting things from the studies is that the kinds of hands-on and experimental, it's dizzy, studies that, it's not quantum specific. And so it doesn't have to be very expensive, complex experimental equipment. Simpler experiments where students still gain that skill of how do I design, a simple electronic circuit? How do I troubleshoot that? How do I measure things from simpler, cheaper equipment? You gain those same skills that we're looking for. So it's not often it's not quantum experiments, it's just experimental skills. So maybe we need to think about, how can we get from lower cost equipment that still have the same outcomes. So I think there's a real opportunity there. It doesn't have to be, building, these fancy sort of quantum experiments.
Sorry. Yeah, thank you very much for your presentation. Now, my concern is marketing of the courses. Ghana here is still really some way to go. So now, when people talk about quantum, hey, what are you saying? You see, so if you want to run a course, like say, quantum physics, to people, some people, unless so very zealous people, what do want to say, okay, a degree or master's say, in lasers and fiber optics. Because lasers, because they are under quantum, so in there they implant the quantum studies or the quantum sciences and all that. Don't you think it would be more marketable this way, particularly in our countries, of course, than yours? Thank you.
Yeah, that's a really good question of how do you, if I understand the question correctly, so how do you get students to want to sort of follow this career path and get engaged in these courses? Yeah, I mean, I think a lot of what we also need to do is think before the undergraduate level and understanding, at sort of the high school and K-12 of demystifying quantum. Quantum isn't this sort of strange thing that there's not going to be any opportunities or has no connection to our daily lives. And understanding that it's just another part of our world, and its relationship to everything we're doing is going to become stronger and stronger. So I think it's not just at the undergraduate level, but also before then, where we need to work to make sure the public understands the importance of this, just like the importance of computers and AI and other things. I think also at the undergraduate level, understanding that taking these quantum courses and things not only prepares you for this hopefully very rapidly growing industry, but also for so many other opportunities, right? It's not too narrow where you can only work in the quantum industry, but if we empower students with these skills, they can go off and work in semiconductors or other technical industry, but they will have an edge because they have this quantum knowledge that can help that company. So I don't know, that's just some of the possible suggestions.
Thanks. Do we have any other questions? Yeah, I got one here.
Hi, thank you so much for such an insightful presentation. So my name is Priscilla Lacham from the African Institute of Excellent Research. And my question is there an international organization dedicated to only quantum sciences, like the International Atomic Energy Agency, which is dedicated to only nuclear sciences? Please, I would like to know.
Yeah, so that's a good question of like where does the quantum, what organization can support these partnerships and so obviously through the International Year of Quantum, UNESCO has started to build these things. I am not aware of one organization that really focuses on this. There are different sort of smaller groups, but I'm not really aware of sort of a worldwide organization that really starting to sort of couple and partner folks on quantum. I think it's needed. I think you bring up a really excellent point.
Yeah, and I think I agree with you, Heather. I don't know of any international. I mean, there's lots of national quantum initiatives which would do that, but I don't know of any global. That's a great point.
We need that.
Yeah, I think we definitely do. Any other questions? Well, I was just going to comment. I mean, everything you said resonated quite a bit, but I remember I started out in a spectroscopy lab, and it was actually a very modern one at the time, but it was back in the early 80s. But I mean, the first thing I had to do was to build a vacuum system. I mean, a rough pump and a diffusion pump, and that went back 100 years or more. So it was nothing very modern about it at all, even though we were pretty much doing quantum physics at the time, I mean, spectroscopy. But and then everything else, I think I was learning how to make electrometers and realizing that, at least at that time, everything that I did as an experimentalist came down to measuring a voltage or measuring a frequency, and those are the only two things you could possibly measure, as far as I knew. And that's all, that probably is true in almost everything you do, right? So basic skills were very important and how to do that. And once I found out about that, when I kind of realized that, it really demystified a lot of experiments of the people down the hall. Okay, what are they measuring, voltage, and when do they do it? So at any rate, I think all your points are really well taken, and I think the idea of translating some of these programs to Africa, also very interesting as a challenge. I know we were here, I was last year, but I mentioned to them in 2004, but we were doing active learning in optics and photonics. And then we really had to think hard about how to make things inexpensive, but still get the ideas across. And then actually in optics, it's pretty easy to do things very cheaply, and really you could even cover things like diffraction very cheaply. So it was possible, and I agree completely with you that it's basically the experimental skills and learning how to work together. Those are the important things, and then just to set the stage. The last thing, I'm really curious, because when you said everybody's looking for PhDs, there's the old kind of quip that managing PhDs is like herding cats. And so is there a management program for how to manage PhD physicists in a company to keep them all moving in line, or is that sort of out of your area?
Yeah, I mean, often it's other PhDs, and yes, people are looking for PhDs, and I do stress that is at certain levels. There really are other opportunities for bachelor's level and master's students. And this idea of collaborative working and leadership, right? Those are skills that transcend quantum and are needed, right? So there are opportunities there as well.
Okay. All right. Well, if there are no further questions, well, thank you again, Heather. That's a wonderful talk. Really very valuable. Let's thank Heather again.